we're going to be taking a look at dipole theory and bond polarity, okay? So we're going to use this table to fill in the VSEPR shapes. So this is going to review our VSEPR shapes. I'm going to draw different variations of our Lewis dot structure diagrams just so that you can see different orientations and different ways that we bond or double bond will still result in the same VSEPR shape. So you should be using X to represent the central atom and A to represent the peripheral atoms when you are doing this. In a linear diatomic molecule, we do not have any central atom, okay? There's no central atom. There's only two involved. There's nobody that's in the middle. So if we were to draw a Lewis structural diagram, there are a couple variations that we can have. For example, if X represents hydrogen bonded to a halogen, it would look something like this. Or let's say hydrogen is bonded to another hydrogen. It would look something like this. Or two halogens are bonded to each other. So there is a couple variations of what a linear diatomic will look like. Now, the key to drawing the VSEPR shape here is that it's linear. So we will use one line to connect the two atoms together. Okay, so those are a couple of our variations. Okay, let's move on to linear triatomic. So we do have a central atom this time, and what we're looking for on our central atom is two bonds and zero lone pairs. Now remember that when you are drawing a linear molecule or whatever Lewis dot structural diagram, double, triple bonds are considered as one connection or one bond when we are doing VSEPR. So let's do some variations. Let's say we have our peripheral atom double bonded to our central atom. Again, even though that's two double bonds, it's still considered as two bonds, two connections to the central atom. Another way that we could do this one is, let's say we have our central atom. It is triple bonded to one of our peripheral atoms and single bonded to another. That's another variation. Oh, this should have some lone pairs on it. Does anybody have any other variation? Not as likely. Not as likely. Okay, so here, our diagram, our VSEPR diagram will look like that. Again, we never show triple or double bonds on our VSEPR diagram. Moving on to our trigonal planar. There are three connections or three bonds, zero lone pairs on the central atom. I need you guys to understand that I am only focusing on the central atom when I am looking at bonds and number of lone pairs. These lone pairs here do not matter, okay? You only focus on the center. So we have our central atom, and we have bonded it, let's say, to three other atoms. This is simulating a compound such as BF3. Another type is we have our X double bonded to one of our peripheral atoms and then single bonded to our other atoms are single bonded. This is simulating something like H2CO. A trigonal planar, X goes in the center and everything has a bond angle of 120 degrees. So keep that in mind when you are drawing this diagram. Remember that those bonds have electrons in them and they're repelling each other. They're trying to maximize their space. So I want you to reflect that in your VSEPR diagram. Okay, tetrahedral. A tetrahedral is usually formed when we are working with group 14 atoms as our central atom. So we have 4 bonds and 0 lone pairs. I'm only going to draw one variation for this one. So we have X in the center, A, 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 A. Okay, notice how there are 4 bonds to our central atom and no lone pairs. Okay, so this is simulating methane. Okay, we can also have halogens because they have a bonding capacity of 1. So we can also have halogens bond to our central atom. Okay, maybe this is simulating something like silicon tetrafluoride. Oh, there should be a 4. That should be a 4. When you are drawing a tetrahedral molecule, you will put the central atom in the middle, and you show the 2 in the plane. So we have A in the plane, and we have another A in the plane. Then you have one that's coming towards you. Okay, we represent with that with a wedge. And then we use a hashed line to represent the atom in the background. Okay, we're going to now move on to trigonal pyramidal. This is when lone pairs become involved. We're going to have 3 bonds, or 3 connections, and 1 lone pair. So, basic example of this is NH3, ammonia. So you have X in the middle, lone pairs, and then you are bonded to 3 other peripheral atoms. Again, it's the same thing. You can have the A's represent hydrogen. You can have the A's represent halogens. Anything with a bonding capacity of 1 can represent the peripheral atoms. Now, when you are drawing your VSEPR shape for this, start off with your central atom. You have one of your peripheral atoms in the plane, one that is coming towards you, and one that's in the background. Notice that, again, no double, triple bonds are represented in VSEPR, and there is no lone pairs on the diagram. Okay, we know that there's a lone pair up here because it's pushing the rest of those bonds down. That's how we know there's a lone pair up there, but we don't show it. The last one is bent. So we have 2 bonds and 2 lone pairs. So the basic shape is we have our central atom. It has 2 lone pairs and 2 bonds. Please, when you are drawing the VSEPR shape for this, you need to emphasize that there is a bend there. If you draw this like linear triatomic, I cannot give you the mark. You have to emphasize that there is a bend. You have to show those molecules being at a bend. So you can draw your VSEPR diagram like this, and I'm okay if you draw your VSEPR diagram like this. VSEPR doesn't matter because it's 3D. These particles rotate in the environment. So it's okay to show it like this, but you need to emphasize that there's a bend. Okay, so here we have a typical numeric response question that we may see on a test. So we have our codes here that are emphasizing what shape a molecule is making. So I'm just going to give you the answer if you want to take a moment to do it. This one is going to be angular or bent. Okay, please know that these have ulterior names. You should know both of them. They have different identities. Ammonium is trigonal pyramidal. Looks like this. Boron trifluoride is a trigonal planar. And CH2F2 is going to be tetrahedral. So your code should be 5324. Okay, so there's the shapes. I highly recommend drawing them on a test just so you are sure when you are filling these things out. Okay, today's learning goals. we're going to determine bond polarity using dipole theory and understand that compounds can be nonpolar even though they have polar bonds, and polar or compounds can be polar even though they have nonpolar bonds. Okay, so we're now going to start looking at the compound as a whole. We're not really going to focus on those bonds anymore. We're going to look at the compound as a whole. Okay, so a dipole moment sorry, no. It's not dipole moment. A net dipole describes the direction of the negative pole in a molecule. Just because there are polar bonds in a molecule does not mean that the molecule will be polar. I want us to understand that whenever I am referring to a molecule, I am talking about a molecular compound. Okay, so whenever I'm talking about a molecular compound, it can also be called a molecule. Before we kind of get into how to determine if a molecule is polar or nonpolar, I want us to see if we can come up with some examples. So take a moment, work with the person beside you, and see if you can come up with nonpolar and polar compounds. I'll give you one example. A polar molecule that we commonly use is water. Now think about things that dissolve in water. Those will be polar. Think about things that do not mix with water. Those will be nonpolar. So take 3 minutes and see what list we can come up with. So here's the examples that we came up with. Not bad of a list. Now here's what affects molecular dipoles. Okay? The first thing is electronegativity of the atom. Electronegativity of the atoms in a molecule. The next is the actual bond dipole moment. So the dipole moment. These are placed on the bonds. This will affect the net dipole. And the last thing that will affect the polarity of a molecule is its VSEPR shape. So these are the 3 things that we will be looking at when we determine molecular polarity. Okay, so I am going to talk about what determines molecular polarity behind the scenes. But I want us to have a general idea before we go in. So there's a general rule that a molecule will be considered nonpolar if there are 4 valence electrons, aka the central atom is from group 4. The central atom is from group 14, or is boron, and they are bonded to the same type of element. Okay, so methane, carbon is attached to 4 hydrogens. That's the same type of peripheral atom. Carbon is bonded to 2 oxygens. The peripheral atom is 2 oxygens. Also, boron, an example is Bf3, will also be considered nonpolar. Okay, I'm going to show you kind of what this means. So let's say we have methane. I draw its VSEPR diagram. Looks like this. This would be considered nonpolar, and I'm going to get into the details of why. As soon as I change one of those hydrogens into something else, let's say, for example, I change this top one here into a fluorine, that's going to shift the dipoles, or that's going to shift the net dipole, and it's going to make this molecule polar. Okay, so this is a very specific requirement. The central atom needs to be from group 14, and it needs to be bonded to the same type of peripheral atom. Same goes on with the boron connected to 3 fluorines. As soon as I change one of these fluorines to something else, it's going to shift the polarity of the molecule, and it will change it to be polar. Okay? Another condition for if a molecule is nonpolar is if each atom is attached to the same type of element. So for example, if we have O2, yes, those are both attached to the same thing, and it forms a nonpolar bond. Therefore, there would be no polarity. Okay, so these are the two requirements. If these requirements are not met, molecule will be considered polar. So this is kind of like an if statement. If it meets these requirements, it is nonpolar. If it does not, then it is considered polar. A very black and white line that I'm setting right now. But I will show you what's happening behind the scenes after this. Okay, so here we have another generalization. This is a table that's found in your textbook. It shows the options or the requirements for having a compound that is going to end up being polar, and it has the requirements for a compound that will end up being nonpolar. Okay, I will leave that with you guys, and you can read that when you're doing your homework. Okay, let's test our skills. Just based on what we've talked about so far, we're going to determine if the following molecules are polar or nonpolar. So this first one here, boron trifluoride, polar or nonpolar? Nonpolar. This is what's happening behind the scenes. So whenever you're showing the behind the scenes or I'm asking you to draw dipoles, I want you to use a VSEPR diagram. So boron is attached to 3 fluorines. Okay. From here, we're going to draw our dipole moment. The dipole moment is based on the electronegativity difference. The larger the electronegativity difference, the larger your arrow needs to be. So fluorine has an electronegativity of 4.0. Bromine has an electronegativity of, boron has an electronegativity of 2.0. Okay, so it's going to be pointing towards fluorine, okay, because it is more electronegative. Same thing, we're going to do that with all of the other ones. Okay, my arrows should be roughly the same size because the electronegativity difference between each molecule and boron is the same. So they should be roughly the same size. Now, why this molecule is nonpolar is, remember how I told you about those bond angles? So because this arrow here is going out at the same strength of 120 degrees, or at an angle of 120 degrees, this arrow is also going outwards at the same strength at 120 degrees, and this arrow is going outwards at the same angle at the same strength. So this is kind of like vector addition. And what's happening is because they're all going out at the same angle with the same strength, they're canceling each other out. And when the dipoles cancel each other out, it becomes nonpolar. couple things to notice here. Behind the scenes, all of the dipole moments, so the highlighted arrows, cancel each other out. Oh, that's an O. That's point 1. Okay, this is one reason why it's nonpolar. Another thing why it's nonpolar, because all of the arrows are canceling each other out, there is an equal distribution of electrons in the molecule. So there are no negative or positive sides in this molecule. That's why it's called nonpolar. It has no poles. It has no positive or negative poles. Okay, the next example here we have C2H2. Based on its chemical formula, is this polar or nonpolar? What do you guys think? Polar or nonpolar? Non or yes? It is nonpolar. Okay, the reason being is because it's carbon attached to the same atom. Let's draw a VSEPR diagram for this. You have your two central atoms bonded to hydrogen. Okay, let's draw our arrows now. Carbon is more electronegative. The arrows are going to be a little bit smaller because the electronegativity difference is smaller. Same thing here. We're going to point towards the carbon. Now, I am not drawing a dipole moment here between the two carbons because they are canceling each other out. It doesn't make sense for me. The electronegativity difference between carbon and carbon is 0. Therefore, I will not draw an arrow. So, these two vectors here are pointing directly at each other with the same strength. If you have -5 and add +5, what do you guys get? You get 0. Same thing happens with vector notation. If you're going if you're going 5 in the positive direction and 5 in the negative direction, they're going to cancel each other out. That's why this molecule is polar. Oh, sorry, nonpolar. It's nonpolar. Taking a look at example C, we have H2S. Based on its chemical formula and what we know, polar or nonpolar? Polar. Let's draw our VSEPR diagram and look at the behind the scenes. So we have sulfur in the middle. Do we know what shape this one's going to make? Bend. Good. Okay, so there is our VSEPR diagram again because it's bent. I need to emphasize that there's a bend there. Some of us gets lazy. Now, who has a higher electronegativity, sulfur or hydrogen? Sulfur. Okay, again, they're about the same strength. I don't think the arrow should be that excessively large. Yeah, hold on. Okay, so here is our molecule. What is the electronegativity of sulfur? 2.6. And what is the electronegativity 2.2 of hydrogen? Which gives me a 0.4 electronegativity difference. Okay, so our arrow is going to be quite tiny, and it's going to be pointing up at sulfur. There. Okay. So now, do you guys see how the arrows are going up at an angle towards sulfur? Do you think these arrows are canceling each other out? No. Because they're not canceling each other out, that's what makes this molecule polar. Okay, so dipole moments do not cancel out. Therefore, there is an uneven distribution of electrons equal distribution of electrons. And this is where we see a shift in electrons, okay? So this is where the net dipole comes in. So let's add these vectors together. Okay, so when you were looking for the net dipole, what you were going to do is add your dipole moments together. So the dipole moments, the first one here looks like this. Okay, so it's representing this one here is this one here. Then we're going to draw the other one, which is the same strength at the same angle in the opposite way. So it goes up like this. Okay? So this one here is this one. Couple things I want to note here. When you are drawing dipole moments, you are always drawing them tip to tail. You are always adding them tip to tail. Now we need to draw our net dipole. Our net dipole, we are going to add it. We are going to close the polygon from tail to tip. So I close the polygon like this. So when I'm drawing my net dipole, the electrons are going towards sulfur, which makes sense because it is more electronegative. Now, up here, we will have where the arrow is pointing to our net on our net dipole. Wherever the arrow is pointing, that's where the electron density is higher. The tail part of this arrow is where there is less electron density. And this is how we form the poles on a polar molecule. So where the tip is, that's going to be the partially negative side of the molecule. Where the tail is, that's where there is going to be our partially positive side of the molecule. Because the electrons are shifting in the direction of the arrow. We are forming a negative and positive pole on the molecule, just like a magnet. We are making a very weak magnet. You do not need to show the partial charges when you are doing the net dipole, but I want you to show the direction. There is no cross thingy at the bottom of a net dipole arrow. So just to clarify some things. The bond between sulfur and hydrogen is nonpolar, or closer to nonpolar. However, because of the VSEPR shape and how the dipoles add up, this molecule is considered polar. So dipoles determine the molecular polarity. Electronegativity determines the bond polarity. Electronegativity difference determines bond polarity. Net dipole determines molecular polarity. All right, I want you to try D on your own, show the dipoles, and show the net dipole. Couple things, let's just clarify. Once you draw your net dipoles, the net dipoles are these guys here. Or sorry, your dipole moment is between the bonds. That's based on your electronegativity. That will determine the strength of the arrow. Then, once we have those, we will use the polygon method to add the vectors. Okay? From there, you will then take the arrow and draw a tail to tip arrow. which determines the net dipole. Just to clarify, this arrow here represents your net dipole. It shows the net direction, the general direction of where the electrons are going. Okay, we do not need to put partially positive or partially negative symbols on this because the arrow itself is representing that. Questions, concerns? Got this? Perfect. Okay, listen. So let's talk about immiscible versus miscible mixtures. Okay? So say I'm mixing things together. The general rule of thumb is when two solutions or whatever are miscible with each other, they're the same type. This goes to a saying that is called like dissolves like. So if you are nonpolar, I can only mix with you, or if I'm nonpolar, only nonpolar compounds can mix with me. Okay? So basically, nonpolar plus nonpolar compounds mix. So let's say we mix oil and Vaseline together. Those things will mix with each other. Don't know why we would do that, but it's there. Or have any of you guys made like an oil hair mask? No? No, listen. So I make like an oil hair mask sometimes. So I mix like olive oil and avocado oil together. Those things mix together. You can't, they don't fight it. Another thing is polar compounds mix with other polar compounds. So let's say I wanted to dilute my orange juice. So I poured water in. That orange juice has no problem. It just accepted the water. It allowed it to be mixed together. Then we have immiscible. Immiscible are when two compounds cannot mix together. They do not mix with each other. And this happens when a nonpolar is combined with a polar compound. These two together do not mix. Have you ever looked at bottles of salad vinaigrette at the store? We all do that. We all go to the aisle of salad vinaigrettes and we look at them, right? Favorite thing to do. Okay, anyways, if you have bottles of salad vinaigrette, next time you look at it, you'll notice that the oil sits on top of the water. Okay, and it always says shake before use. Okay, it's because oil and water don't mix with each other. Oil is nonpolar and water is polar. They don't like each other. So briefly, before you eat your salad, you're going to shake it real hard and then pour it onto your salad. But then as soon as you let that salad dressing sit again, it's going to separate because they don't like each other.